page 106, finishing off section 2.5, picking up in the middle of 106 with continuity on an interval. A function doesn't have to be continuous everywhere to be continuous. We can have continuous from the left and from the right, like we finished off with yesterday. We also can have continuity on an interval, like the square root of x, right? We know the square root of x isn't continuous everywhere. It doesn't even exist everywhere. But if I think about the informal definition of continuity, meaning where could I draw this thing without picking up my pencil or pen? I could draw that from 0 to infinity without picking up my pencil or pen. So I could say, okay, this is continuous from 0 to infinity. It is continuous on that interval. That's continuity on an interval. But I'm going to have to redefine continuity for an interval a little bit differently than I do regular continuity. In the middle of 106, it says a function is continuous on an interval if it's continuous at every number in that interval. If the function is defined on only one side of an endpoint. Now, our endpoint here is 0, and that function is only defined on one side. From the right-hand side at 0, it's defined. From the left-hand side, it's not defined. It doesn't even exist. So it says, if the function is defined on only one side of an endpoint of the interval, then we're going to understand continuity at that endpoint to mean continuous from the right or continuous from the left only. So when we're saying that this is continuous at 0, it is sufficient that it's continuous from the right as opposed to being continuous from the left and from the right. Because typically when we're doing continuity, the second part of the definition is that the limit exists. This limit doesn't exist at 0. It only exists from the right. It's only continuous from the right. So continuity on an interval is going to allow for that. All right, so look at example number 4. Example 4 says, show that this function f of x is equal to 1 minus the square root of 1 minus x squared is continuous on the interval from -1 to 1. So they're telling me where it's continuous, but they're asking me to prove it or justify it like I would do for AP. So we could go through first off and say, okay, number 1, is the function defined? Is f of a defined? Well, I'm going to need to think about then the domain of this function, right? Because I could say that it's defined anywhere I don't get 0 in the denominator or a negative under like a square root or a fourth root. I do have a radical here, so I need to stop and think about where does this exist? What is its domain? So I could say, okay, whatever's underneath the radical has to be greater than or equal to 0, and that's a polynomial inequality that we've done previously this year. Set it equal to 0 to get your critical numbers, make a sign graph, pick a test point, and the sign's going to change at each of my single critical numbers. So once we get our sign graph, we can easily see where it's greater than or equal to 0. That's just this piece from -1 to 1. So yeah, that function is defined from -1 to 1, and that was where they were asking me to check continuity. So I can find f of a. So I'll go through. F of a says put a in the place of x. So I'll put a in the place of that x, and there's f of a. All right, second part of the definition of continuity is I need to see that the limit exists. So I need to go through and find the limit, and I'm going to use my limit laws that we've already learned. The first thing that we learned was that if you're trying to take the limit of two things that are being added or subtracted, you can break that into two separate limits and then do your addition or subtraction. So that's the first thing I've done. The second thing I did was remember that when you have a limit of a radical, you can take the limit of what's underneath the radical first before you do your square root or cube root or fourth root. So that's the second limit law that I've applied here. So we can say that the limit of a constant is that constant, right? So the limit of 1 would be 1. And over here, the limit of a polynomial, because 1 minus x squared is a polynomial. How do I find the limit of a polynomial? Direct substitution, right? It's well behaved. So I could go through then and say the limit of the constant is the constant, and the limit of the polynomial, I can use direct substitution, so I can put a in the place of x. So that would be the square root of 1 minus a squared. If I could simplify that, I would, but I can't simplify that down any further. And remember, the third part of the definition of continuity is that f of a is equal to the limit as x approaches a, and I did get those two things to be equal, so I've justified it. I found f of a, I found the limit, and they are equal to each other, so yes, it is continuous on that interval. All right, look at example 5. A couple of theorems that they give us on page 107, and before we get to example 5. On 107, they talk to us about combinations of functions. Remember combinations where we went through and we did f plus g, f minus g, f times g, f divided by g, and we did the domains of those and we multiplied them by constants and that type of thing. On the top of 107, they just tell me that if you have a combination of functions, f plus g, f minus g, f times g, f divided by g, or a constant times your function, that if f and g are continuous at a, then that combination will also be continuous at a. And then a little further down on 107, they tell us that any polynomial is continuous everywhere. That is, it's continuous for all real numbers, negative infinity to a positive infinity. And any rational function is continuous wherever it's defined. So it's going to be continuous over its domain. Now, even though they've just stated that for me, so example 5 asks us to find the limit as x approaches negative 2 of this rational function. Now, remember we have limit laws about rational functions, right? Rational functions are well behaved within their domain. I can just use direct substitution and plug in. So if I go through and I use direct substitution, I can find out that that limit is equal to negative 1 over 11. So here's the cool thing. On the top of page 104, they had told us that we had learned that a function that can be a limit that can be calculated by just plugging in the value of the function at a, we had learned that that was called well-behaved, and we had some limit laws that told us when things were well-behaved. On the top of 104, they told us that that was also the same thing as continuity. So I can use these two things to my advantage. If well-behaved and continuous are similar ideas, then I can use continuity to help me evaluate a limit, or I can use limit laws to help me look for continuity. So here, I could use either one of those ideas. I could say a polynomial or a rational function is well behaved, or I can say if it's continuous at a, it's also well behaved at a. So now, if I show continuity, I can assume that it's well behaved. So those two things will work together and really help me. Not only are polynomial functions well behaved, continuous for all real numbers, rational functions are well behaved, continuous for all values in their domain. But think about some of the other limit laws that we had already learned. We learned that root functions were well behaved as long as I got a value under the radical that was greater than 0. Because of our redefinition of continuity on an interval that we talked about on our first example today, then we can say that root functions, radicals, are going to be continuous on their domain. We won't have to exclude that value with 0 under the radical, because again, we're only looking for continuity from one side when we're looking on the interval. We also can state that trig functions are continuous at every number in their domain. So from this point forward, when they say prove continuity, and almost every theorem we're going to have from here on out is going to start with if the function is continuous. So we're going to have to prove continuity nonstop as part of our justification. I won't have to go through the 3-step definition if it's one of these things. If it's a polynomial, my justification is just all polynomials are continuous everywhere. If it's a trig function, I'm just going to say all trig functions are continuous within their domain, and this is the domain of this function, therefore it's continuous there. Okay, so that'll be a big time saver for me. So example number 6, they asked me to tell on what intervals each of these functions is continuous. So for the first one, what is that, x to the 100? What is that? Polynomial. So polynomials are continuous where? Everywhere. So that's going to be the interval on where that is continuous. Negative infinity to positive infinity. All right, what is g of x? What type of function? Yeah, rational. So what's the rule for rational functions? Continuous within their domain. Right, so I just need to find the domain of this thing. Domain is all real numbers except for where I have 0 in the denominator or negative under a radical like a square root or a fourth root. So we're going to need to say our denominator can't equal 0. So x squared minus 1 can't equal 0. So what are we going to have to exclude? 1 and negative 1. Right. So we could give that an interval notation where we're excluding 1 and negative 1. All right, look at the next one. For h of x, what type of a function is that? It's actually a combination, right? Remember we had that rule about combinations back on the top of page 107, that if you had the combination of two functions that were being added or of two functions that were being subtracted, that wherever the original functions were continuous, then the combination would be continuous, right? So in essence, when I'm looking at this, I'm going to need to find the domain of each piece of the combination, and it's going to be continuous where all three of those domains intersect. All right, so let's think about the domain for this guy. What is this? Yeah, it's a root function, and we've said that root functions are continuous within their domain. So for the domain, we're going to take what's under the radical and set it greater than or equal to 0. So 0 to infinity. All right, what is this? Rational. Rational functions are continuous within their domain. So what do I have to exclude? 1. What is this? Rational. So rational functions are continuous within their domain. What do I have to exclude? Nothing, right? Because this one, if you have x squared plus 1 and you set it equal to 0, you get imaginary. So there's nothing that we have to exclude. Now, they did not ask me to justify this domain, but I will ask you to justify this domain on your test. And there are 4 parts to this justification, all right? The first part is you're going to say that this is a root function and root functions are continuous within their domain, so it's continuous from 0 to infinity. This is a rational function. It's continuous within its domain. Its domain is all real numbers except for 1. This is a rational function. It's continuous for all numbers in its domain. Its domain is all real numbers. And here's the fourth part, which is one of the most commonly missed things on this test. You also then have to state the rule about combinations, right? Because it's not enough to talk about each of the individual components. What makes the combination of those things continuous? So I also need to state something about that rule on the top of page 107, that if f and g are continuous, then if you have f plus g, it is also continuous. Okay? So I need something about the combination there. So for that guy, if I were going to give my domain, again, we said it's the intersection of these 3 domains. So that would be my domain, but that would be the justification that would go along with it if they asked me for a justification. All right, then they talked to us about compositions of functions on the bottom of 109 and the top of 110. So on 109, they basically say if I have a composition of 2 functions, that I can find the limit of the inside function first and then take the outside function, as opposed to having to take the limit of the whole thing. It's kind of like, you know how when you have a limit of a radical, like we did up here, that instead of taking the limit of the radical, you can take the limit of what's under the radical first and then do your square root. It's the same idea. If you have f of g of x, instead of having to take the limit of that whole thing, you can take the limit of g of x and then take f of that answer. On the top of 110, they give us a continuity rule about compositions. And it says if g is continuous at a and f is continuous at g of a, then the composite function f of g, which is f of g of x, will be continuous at a. So if g is continuous at a, your inside function, if it's continuous at a, and if f is continuous at g of a, so once you do g of a, if f is continuous there, then your composite function, f of g of x, will be continuous at a. So in example 7, they give me a composition of functions, one function plugged into another. I'm going to have to decompose it to be able to figure out its continuity. That's why when we did compositions of functions, they made us practice decomposing them, breaking them back apart. So if h of x is equal to f of g of x, I'm going to have to break that back apart and say, okay, well, g of x must have been x squared, and it got put into the f of x function, and so f of x would have been sine x. So I'm going to break those back apart, all right? In order to figure out continuity for that composition, it says, first off, it's going to be continuous at a if g is continuous at a, the inside functions. Let's start with the inside function. The inside function was x squared. So where is that continuous? All real numbers, right. My justification would be all polynomials are continuous everywhere, right? So then I would have to look at, I'm going to plug g of x in the place of x. So basically I'm plugging all real numbers into the sine function. So I'm taking the sine of all real numbers. So what is the rule about trig functions? They're continuous for all values in their domain. What's the domain of the sine function? All real numbers, right. So if I put all real numbers in the place of x, I'm just going to be taking the sine of all real numbers, and sine is continuous for all real numbers. So I could say, okay, then that domain is going to be all real numbers. And so they had told me then that my domain for my composition would be where those two things intersected. All right, so justification. 3 parts, not 2. I'm going to have to justify this part. All polynomials are continuous everywhere. I'm going to have to justify this part. All trig functions are continuous within their domain, and the domain for sine is all real numbers. And then here's the part that most people forget and leave out on the test. I also have to justify the composition. I have to state that because this was a composition of f of g of x, according to that theorem on the top of page 110, because g was continuous at a and f was continuous at g of a, then the composition f of g of x is also continuous at a. Okay? So that is the fun part about AP Calculus, right? It's not enough that I come up with the right answer. My right answer is all real numbers, but then I have to go back and I have to justify, I have to recognize that there are 3 components of it that I'm using, and I have to justify all 3 components. That's the extra that we put in for our AP. Okay, over on page 111, they talked to us about the intermediate value theorem. Now, we learned the intermediate value theorem last year in pre-calc. But it says that suppose f is continuous on the closed interval AB, let n be any number between f of a and f of b, then there exists a number c in that interval from a to b such that f of c is equal to n. The short version of that is that if n is a number between f of a and f of b, there's a y value in between f of a and f of b, then there has to be an x value in between a and b that goes with that, right? I mean, you can't have a y without having an x. And we apply the intermediate value theorem to help us solve all kinds of different things. And here's something that we can utilize it to help us solve. Example 8 says, show that there is a root of this cubic equation between 1 and 2. All right, if I'm going to apply the intermediate value theorem, it starts off by saying, suppose that f is continuous on the closed interval. So the first thing I'm going to have to do is prove continuity. So what's my rule for continuity? What is this? A polynomial. So what's my rule for continuity? All polynomials are continuous everywhere. Okay, so I'm good. I'm continuous. I got to check that first because I can't use the intermediate value theorem if I'm not continuous. All right, so since I'm continuous, I could go through the second thing that I'm going to want to look for to prove that there's a root here is I'm going to want to look for a sign change. If you think about it, if I plug in 1 and I get -1, and I plug in 2 and I get +12, there's a sign change there. How do you move from a negative value to a positive value without going through 0? Or how do you move from a positive value to a negative value without going through 0, right? So here's how the intermediate value theorem can help me. Because I've got a sign change, I'm going to start off by the first part, continuity, right? I'm going to say since f of x is a continuous function and n equals 0 is a number between f of 1 and f of 2. How do I know that? Well, because like we just said, there was a sign change here. In order to go from a negative value to a positive value, you have to go through 0. Or in order to go from a positive value to a negative value, you have to go through 0. So because I've shown there's a sign change, I can say, okay, n equals 0 has to be a number in between f of 1 and f of 2. Then according to the intermediate value theorem, if there's a y value of 0 in between f of 1 and f of 2, then there has to be an x value that goes along with that. So there would have to be an x value, call it c if you want to, in between 1 and 2 so that f of c is equal to 0. And so that would be my justification that there is at least one root between 1 and 2. There might be more than that, but there's at least one. So that's how the intermediate value theorem can help me with my justification there. Okay, so here is our homework for tonight on pages 112 to 113.